Okay, so is there anyone in this live session? Should I wait for someone to join? Wait for a few minutes, then I will start. In this course of Physical Chemistry 1, uh, which is running in the 9th week, I think, you have done the course, all the 8th week is completed. Your assignments is also over. So a brief summary of the course is that we have started talking about the pre-quantum concepts. And I said you that what were the issues related to the classical mechanics and what were the observations which could not be explained in classical mechanics, and then how these problems were tackled by applying the concept of quantization by Max Planck. And the first concept we talked about was black body radiation, where the Max Planck gave his idea of quantization and his famous equation of E is equal to h nu. And then these quantization concepts and E is equal to h nu was used for dealing with other concepts also, which were not explained in the classical mechanics, like specific heat of monoatomic solid, the results of the photoelectric effect, which were not in conformity with the classical mechanics, and then line spectrum of hydrogen atom, which was known but it could not be explained in the classical mechanics, and then Compton shift also. So in all these cases, the concept of quantization given by Max Planck was used, and it got established that quantization takes place. Thereafter, the thereafter we talked about postulates of quantum mechanics. And I said you that when Schrodinger gave his equation, d square psi by dx square plus 8 pi square m by h square e minus v psi is equal to 0, and he tried to apply, for applying the Schrodinger wave equation and for getting the wave functions, he put forward, there are several postulates which are basic to the quantum mechanics. Without these postulates, you cannot apply Schrodinger wave equation to any system. So we talked about these postulate 1, 2, 3, 4, and 5. Each one describes one particular concepts of quantum mechanics. The first one is wave function. Second one is the operator. Third one is the eigenvalue equation. Fourth is expectation value. And the fifth is time-dependent Schrodinger wave equation. Okay. So in postulate one, in wave function, what you say that every system is characterized by a wave function. This wave function is a mathematical function which has variables, and these variables could be coordinates or time. So if you remove the time, then you get a time independent wave functions, and if you keep the time, then you have time dependent wave functions. In most of the lectures in this series, what we have used is time time independent wave functions without time. Okay, these wave functions are mathematical functions. It could be a real function, it could be an imaginary function. So that also I talked about. And if it is an imaginary function, the square of the function it becomes real in the, as I have shown it here. Okay, psi is a mathematical function which could be a exponential function, which could be a trigonometric function, which could be exponential function like this one. Okay, so if this is your complex function, complex variable z is equal to x plus iy and z star is equal to x minus iy, then z star becomes x square plus y square. But all mathematical functions are not acceptable in quantum mechanics. So there are certain criteria which a wave function must fulfill, and these criteria are that psi should be either real, or if it is imaginary, it should be able to be convertible into the real functions. Then psi should be finite, psi should be single valued, psi should be continuous, psi should be square integrable, and the slope of the wave function should also be continuous, provided there is no sudden jump in the potential. Okay. Then for just for the sake of your convenience, here are some of the wave functions which I have written the reason why it is acceptable, why it is not acceptable. Okay. Say the first function psi is equal to x is not acceptable because psi at infinity, psi is infinity at x is equal to infinity. But psi is equal to, I think, come down to here, minus exponential minus x square is acceptable because psi is not equal to infinity at both x is equal to plus minus infinity. Okay. So these are the certain wave functions which tells you that how to check that whether a particular wave function is acceptable or not acceptable. Okay. Once you have the wave functions, then what does this wave function means? What is these are some graphical representations which tells you which function is allowed, which function is not allowed, means which function is acceptable, which function is not acceptable. Then thereafter, the physical interpretation of the wave function is that wave function in itself has no physical significance, but the square of the wave function is equal to the probability density. So psi star gives you the probability density, and psi square it also gives you the probability density if psi is real, if psi is complex. Okay, but if you multiply by a volume element, this density gets converted into volume after multiplying the volume element. What we get is probability density becomes probability. So psi star d tau gives you the probability of finding a particle. And now if you integrate this psi star d tau over whole space, then it means the particle is present within the whole space. So probability over whole space will become equal to 1. Okay, and we say such condition to be normalized condition. Okay, so and if your this integral does not comes out to be 1, then then it means this wave function is not normalized, and you need to normalize it. For normalization, there is a procedure that you multiply the wave function by a constant n, and then you use the normalization condition to find the value of n. So for example, if you have a function exponential I m phi, then you multiply it by n, it becomes n e m phi exponential I m phi, and since phi the condition is given that the value varies from 0 to 2 pi, so minus infinity for this is 0 and plus infinity for this is 2 pi. So you integrate this function from 0 to 2 pi, and what you get is 1 over root 2 pi as the value of n, and your normalized wave function becomes 1 by root 2 pi exponential I m phi. This we have already done in case of hydrogen atom also, and at other places also. So normalization procedure is an important concept in the quantum mechanics, and that you will have to always do when you deal with any system for which you apply Schrodinger wave equation to get a wave function. What you get is actually not a normalized wave function, it's an unnormalized wave function, and separately you have to normalize that wave function. Okay. Another concept for the wave function is the concept of orthogonality. which says that psi I psi j d tau is equal to 0, means where I and j refers to two different quantum states. Okay, so if you're multiplying two different quantum states wave function psi I and psi j, and by definition a square of the wave function should give you the probability density, and multiplying by the volume element it should give you the probability, then what exactly we can say it, we can stretch it to the limit to say that not exactly, but what we are saying is that we are finding out the probability of finding a particle within the same at the same time, a simultaneous presentation of the system in two different quantum state. And this in itself is an impossible thing. A system cannot exist in two different quantum states simultaneously. So this integral has to be equal to 0, and this is called orthogonality condition. So if you have a system where the system has different states, then each of these different states will have a separate existence. And if you try to find out this integral psi I psi j d tau, then this comes out to be 0. You can combine these two conditions, orthogonality condition and normalization condition, to get an orthonormal conditions. An orthonormal condition is shown by Kronecker delta. It is the same thing that if I is equal to j, del ij becomes equal to 1. If I is not equal to j, then del ij becomes equal to 0. Okay. So this is all about the first postulate, wave function. In the second postulate, we talk about the operators, and this operator is a symbol, is a mathematical symbol which tells you to do some mathematical operations. As for example, a symbol of multiplication, a symbol of addition, a symbol of square root, a symbol of differentiation, a symbol of integration. It could be anything. Okay. When you operate with an operator on a function, the function changes. Obviously, if you take the square root of 25, it will become 5. So the function changes. 25 is your function, and mathematical operation is a square root. So if you take the ddx of x raised to the power x squared, then it becomes 2x. So the function changes. So when this tells you that when you operate with an operator a on a function fx, it becomes gx. Okay. Or other way is that if you operate with a function a on a function fx, then you get a constant a multiplied by function fx. Okay. So both are possible. You get a different function or you get the same function back with a constant value. Okay. These operators are normally given a symbol, a hat or a tilde. These are the symbols. If this symbol is present on anything, it means it represents a quantum mechanical operator. In quantum mechanics, for every physical variable, there is a specific operators. So for example, if you talk about position, then there is an operator for position which is just multiplication by x. If it is r multiplication by r, very short, this table is a very short table. You will get a long table in quantum mechanical books. Okay, just to tell you the quick revision of the things which we are doing. If any one of you are here and you want to you have any query, please stop me and ask your queries. Okay. Then we have x component of momentum, which is given as minus I h cross ddx or h cross I divided by I ddx. Then kinetic energy is given as minus h cross square divided by 2m d square by dx square. Then total energy operator is given as minus h cross square divided by 2m d square by dx square plus v, where v is the potential energy. Okay. So such tables you will get in quantum mechanics, in any quantum chemistry book. Okay, a long table which will give you all the quantum mechanical operators. Okay. There is a certain set of rules with which the operators are operated on a function, and that's called algebra of operators. We say addition and subtraction of operator is that if you have a operator and b operator and you operate with a sum of these operators, then it must be equal to the operation by these two operators on the function, and after operation, if you sum it up, you should get the same result. Same way for multiplication, we have the rule that if you have 2, 3, 4, 5 operators in a sequence, then always the sequence is that the rightmost operator from right to left. You have to operate from right to left. The right operator is B. So first you operate with B and then you operate with A. If you have a square of an operator, then it means operating with the same operator twice. Okay. If if you have a raised to the power n times, you have to operate on a function fx. Okay. Then operators obey associative law of multiplication. This also is same as the algebra results. Then another concept and operator is that of commutator, which is very important in quantum mechanics. If you operate with I said you have to multiplication of operator tells you that if you have two operators A and B, then you have to operate in sequence. Means first you operate with B and then you operate with A. You could have operated first with B, first with A and then with B. If you do this way, means if you operate AB operation and BA operation and you get the same result, then we say the operators A and B commute with each other. And if they do not give you the same results, means AB minus BA has non-zero values, then we say A and B do not commute with each other. And this difference is called commutator and is shown as a bracket like this one, AB commutator. Okay. AB commutator is that you operate AB first and then you operate BA first and then you subtract AB minus BA. Same way you can write BA commutator is BA minus AB. So it will be different. Okay. So concept of commutator is very important in quantum mechanics. We have talked about in the course in details. Okay. Then after this, well, we have the two concepts are linear and Hermitian operators. A linear operator is an operator when if you operate with an operator on two functions fx and gx, sum of fx and gx, and if you operate on the function separately, afx and gx, and you sum it up and you get the same result, then you say it's a linear operator. Or if you have an operator, you operate with an operator on a constant multiplied by a function, okay, then it should be equal to constant multiplied by operation of an operator a on the function. Okay. If these two criteria are met, then we say it's the linear operator. And the example of linear operator is ddx, ds square by dx square, and x square also. Some of the non-linear operators with which you are familiar is squaring the number and taking the square root of the number. If you square it, you don't get the same value separately, and some of the numbers, if you square, you don't get the same value. If you take a square root of 16 and 19, you don't get the same square as the square root of 25. So these two, taking a square and taking a square root, are non-linear operators. Okay, so this gives you a clear concept of which is linear operator. Then we have the concept of Hermitian operator in quantum mechanics, which is like this one, that if the integral psi star a phi d tau changes to phi a star psi d tau, then you take the complex conjugate of a and complex conjugate of psi star. Then if the operator a obeys this law, obeys this condition, then we say it's a Hermitian operator. You see what I have done here is that if I write the three things, 1, 2, and 3, then you replace 1 with 3. 1 goes to the third position, 1 goes to the third position, and 3 goes to the 1 position, and then you take complex conjugate of this first one. Okay, complex conjugate of the operator also. The first one was already there. So you can write it like this also, a psi complex conjugate. So if an operator a obeys this condition, then we say it's a Hermitian operator. And in any quantum chemistry book, if you open the book and you find a table of the operators, then all those operators are linear Hermitian operator, which is written there. One easy concept is this one. But we can find out that whether an operator is a Hermitian operator and not a non-Hermitian operator or anti-Hermitian operator, okay, or non-Hermitian operator. We can do this. But the single concept which you must have in your mind is that every operator which is given in the table is always linear Hermitian operator. In quantum mechanics, whatever operator we are using is a linear Hermitian operator. The reason for this is that Hermitian operator always gives you the real number. I have talked about in details in the course lectures. Okay, here I will not talk about the details. So if you have to check whether the particular operator is a Hermitian operator or not, then we give the concept of a dagger operator, which is actually a Hermitian adjoint. Hermitian adjoint is taking the transpose and then taking the conjugate. Okay, so if this is your Hermitian adjoint a dagger, then if a dagger is equal to a, we say a is a Hermitian. If a dagger is equal to minus a, we say a is anti-Hermitian. And if a dagger is neither equal to a nor equal to minus a, then we say it's to be non-Hermitian operators. Okay, and if, for example, some of the rules for finding what the dagger operator is, that you have these rules. A dagger is A, AB dagger is A dagger, B dagger, A plus minus B dagger is A dagger plus minus B dagger. A small a dagger, A into A dagger is equal to A complex conjugate of A and then A dagger. Okay, so these are the 7 rules which you have to follow. And with this rule, if we go for the simplest operator, that is momentum operator, minus IH cross ddx, and we find out the dagger of this, then px dagger will be minus IH cross ddx dagger, and minus IH cross dagger or ddx dagger we can write. And so applying the rule number 4, minus I H cross will be minus I H cross star, and then dx dagger. So minus I H cross dagger will become equal to I H cross. Sorry, there is some mistake. It will be I sorry. Okay, so I will continue from here. There's a mistake. Then this will be plus IH cross, and this will be minus ddx. Then this will be equal to px only. Okay, so this will become px, that will become into px. There is some mistake here, so don't go for this one. Okay. I'm omitting it, and I can write it IH cross, and then it is minus ddx. Okay, so this will become equal to minus IH cross ddx, and this will be plus px. Okay, so there is no need to write plus minus. Okay. It will be equal to px. Okay, so px dagger is equal to px, and then px becomes equal to px is a Hermitian operator. Same way, if you have IH cross d square by dx square, then this a becomes equal to minus a, and if a becomes equal to minus a, it's a anti-Hermitian operator. So we can check it through the using the Hermitian adjoint. But in any exam, if you find an operator which is the same operator which you have seen in your book, then blindly you can say it's a Hermitian operator. Okay, so don't get confused about it, because all operator in Hermitian in quantum mechanics is Hermitian. And why do we use Hermitian operator? Because Hermitian operator gives real eigenvalues. Okay. The third postulate is eigenvalue equations, where you operate with an operator on a wave function and you get a constant and a wave function and the same function back. Okay. If it is so, then we say such wave functions to be eigenfunctions and such constant to be eigenvalue constant. So if you operate with an operator A on psi and you get a constant multiplied by psi, then this operator A is operating on a function which is called eigenfunction, and this small a, which is a constant, is called eigenvalue. So if you don't get the same value, if you operate with an operator A on a function psi, you get a constant, but your function becomes phi, then this psi is not an eigenfunction. This is not an eigenfunction. Okay, which I have written now. Psi is not an eigenfunction, but this is an eigenfunction. So all wave functions are not eigenfunctions, but all eigenfunctions are actually wave functions. Then the fourth postulate, the summary was that if you have to calculate the expectation value or average value of a particular property, physical variable, then you use this Rayleigh ratio psi m psi star data divided by psi star data, and you can get the average value of or expectation value of a particular physical variable. Then we have time dependent Schrodinger equations. The last postulate is h psi is equal to I h cross divided by 2 pi del psi by del t, which we will not use throughout this course. Okay. With these five postulates, this is this fifth postulate, 5 postulates, we can apply Schrodinger wave equation, and we did apply Schrodinger wave equation to particle in a one-dimensional box. This was your box where the particle is free to move on this line, 0 to a line. Okay, and we suppose b is equal to 0 inside the box, outside the box it's infinity, and we got to the wave functions. What actually we got is psi is equal to a sine n pi x divided by a. Okay, but the value of a, which is the normalization constant, we find, and we find out psi is equal to root 2 by a. So root 2 by a is the normalization constant, sine n pi x divided by a is obtained. And similarly, the energy is obtained where n is equal to 1, 2, 3, 4, and so on, integer values. So the energy which we obtain in particle in a one-dimensional box is n square h square divided by 8 ma square. Okay, and so if you put this value, the energy for the first level will be h square divided by 8 ma square for n is equal to 1. For n is equal to 2, it will be h square divided by 8 ma square multiplied by 4. For n is equal to 3, For n is equal to 3, it will be 9 h square divided by 8 ma square, and so on. This we all obtain. So the application of Schrodinger wave equation, the Schrodinger wave equation which we applied to this system was d square psi by dx square plus 8 pi square m by h square e psi is equal to 0. If any one of you is live in this class, you have joined, then please tell me your issues, your problems. Okay, since no one is here, so I am repeating what you have already done in the previous weeks. Okay. So this is the problem, the first problem which we deal with in the course. Then the second problem was particularly in a three-dimensional box, and for which the result I have written here is the concept of degeneracy. If it is a cubical box, then the wave function comes out to be sine is equal to 8 divided by a cube, sine nx pi x divided by a, sine ny pi y divided by b, a, and sine nz pi z divided by a. Okay. On the energy value or the eigenvalue comes out to be h square divided by 8ma square, nx square plus ny square plus nz square, where all these nx, ny, and nz refers to quantum number and varies from 1, 2, 3, so on. Nx also, ny also 1, 2, 3, and nz also 1, 2, 3. And from this application of Schrodinger wave equation to three-dimensional box, we learned the concept of degeneracy. That okay, if you have E112, then its energy should be equal to E121, and its energy should be equal to 211. But each of these energy value represents different quantum states because the wave function will be different. So what I have written here is E nx, ny, and nz. If you put this nx, ny, and nz value here in the wave function, then you will have a different psi 112, psi 121, and psi 211. All three will be different wave functions representing the degenerate states. Okay, so all three quantum states with the same energy value, we say such states to be degenerate states. So the concept of degeneracy we learned when we were talking about three-dimensional box model. Okay. After this, I talked about since we in a particular in a one-dimensional box, we have the boundary where the potential energy becomes infinity on both sides, x is equal to 0 also and x is equal to a also. So it was essential to learn that if the boundary is not infinite, what will happen? So we talked about the finite boundary condition, and in finite boundary, in a potential well like this one, we can have two different. The left hand side is same, v is equal to infinity, as we did in particle in a one-dimensional box. But on the right hand side, region 2 is different. We have a potential there. So if we apply the Schrodinger wave equations to region 1 and region 2, and finally what we get is a plot like this one. We get this equation and a plot like this one, where we say that these lines are the plots of LHS equation and these lines are plots of the RHS equation. So there are three different points in this diagram where LHS and RHS becomes equal. So at these specific values of energy only, above equation is satisfied. What does it mean? It means that the discrete energy levels are present for a specific value at a specific value of energy, because only then these equations will be satisfied. Okay. So quantization results comes here also, but the wave function, if you plot, it goes beyond the boundary also. You look at this one. This is the boundary, and the wave function goes beyond the boundary also, in contrast to what you have done with the infinite potential wave. If you have energy, if you have another kind of potential like this one, in between these three regions 1, 2, and 3, we have a potential wall. So if you look at the three regions 1, 2, and 3, then first region and the third region, since we have taken v is equal to 0 and v is equal to 0, so they are same. Okay, and for the second region, we can write E minus v is equal to 0, and it can give you a psi2 value like this one. Okay, and from this this equation I've given you, that the three equations, what are the A exponential I k1x tells you that the particle is moving to the right, then B exponential minus I k1x, reflected wave moving in the left direction in the region 1 only. Then in region 2, we have C exponential k2x, barrier wave moving right. So within this barrier, if the wave enters, then it's moving in the right direction. Then D exponential minus k2x tells you barrier wave moving in the left direction. Then if the wave crosses this potential bar or this potential barrier, then we say the transmitted wave is f is equal to exponential I k3x, and this g exponential minus I k3x is incident wave moving to the left, which is known. Okay, so that and we calculated the transmission probability of a wave from first region to the third region, and we got this equation. And this equation tells you, this equation tells you that the transmission coefficients depends on the width of the energy barrier, height of the energy barrier, and mass of the particle. Because you have the mass of the particle, okay, you have the width of the barrier, and you have the energy of the barrier. Okay, so all these three factors decides the transmission probability, and this effect is called electron tunneling. And this electron tunneling diagram tells you that if you have a wave which travels from first region to third region, then this is your tunneling, which is shown here. Tunneling is shown here. And if the wave has a higher energy, then there is no point. Your barrier is low, so it can cross through this region also. Okay, so it's same region for similar thing for all these cases. If the energy is high, then and potential barrier is low, then the wave can cross easily. But even if there is a potential barrier, then also some wave can cross this potential barrier, and this is called tunneling. This which has a very wide-ranging applications I talked about in the lectures. Okay. Then we talked about simple harmonic oscillator, and I showed you that the energy for this simple harmonic oscillator is h nu is equal to v plus half. And so the concept of zero-point energy came into existence, and this was a simple harmonic oscillator. Okay, and this harmonic oscillator gives you an energy for the ground state, for the first excited state, third excited state, and the difference between the energy levels is h nu, and h nu, h cross omega, h cross omega, h cross omega. So we talked about this one in details. Okay, this concept of simple harmonic oscillator is important because this forms the basis of IR spectroscopy. Okay, in IR spectroscopy, you say that molecule is vibrating. So a vibrating molecule will have if it has a harmonic potential, which we say the potential energy for the this is equal to 1/2 kx square, a harmonic potential, then it should look like this one. It should have these energy values for the different eigenstates, and this energy states is called will lead to IR spectroscopy for a particular covalent bond which is vibrating. Okay, so the simple harmonic oscillator is the basis for IR spectroscopy or vibrational spectroscopy. Okay, here also we applied the Schrodinger wave equation, and the application became more complicated here, and we use the concept of Hermite polynomial in these applications, and finally we got the normalized wave functions like for the ground state it was beta divided by pi raised to the power 1/4 exponential minus beta x squared divided by 2, and for other states, higher states also, we got the normalized wave functions for the harmonic oscillator. Okay, if not all, then at least the first eigen functions, that's ground state eigen functions, you must remember what is the value of beta, what is the value of ground state wave functions. Okay, of course eigenvalue you always remember because you read it in your vibrational spectroscopy also, or zero-point energy concept of zero-point energy, but eigen functions also you remember at least for the ground state. Okay, so this was the salient features of the graph which I have shown, that what is the application of Schrodinger wave equation to simple harmonic oscillator, and how does the wave functions looks like. We have already done it, in your course. So I will move ahead. In case of hydrogen atom, we came with the concept of applying Schrodinger wave equation in spherical polar coordinates. For the first time, we did in rigid rotor, and in case of hydrogen atom also, we apply in spherical polar coordinates. So you can convert the spherical polar coordinates into the Cartesian coordinate into spherical polar coordinates, means x, y, z into r, theta, and phi, where r has the limit of 0 to infinity, theta has the limit of 0 to pi, and phi has the limit of 0 to 2 pi. Okay. Z is equal to r cos theta, y is equal to r sin theta sin phi, and x is equal to r sin theta cos phi. So these three equations are important, which you should remember. Okay. So these three equations are important. Z is equal to r cos theta, Z is equal to x is equal to r sin theta cos phi, and y is equal to r sin theta sin phi. So what we did is we wrote the Schrodinger wave equation in spherical polar coordinates, and then we applied the concept of separation of variables, and we separated it into three independent equations. And these three independent equations which we obtained were phi equations, theta equations, and r equations. I think there is some issue related to the presentations. Okay. What's happening? Let's stop sharing. Okay, anyway, I think my system is the system has hanged, but anyway. So we talked about hydrogen atoms, and in hydrogen atoms there's some issue with the computer center itself. Okay. So when we did this one, when we separate this equation into three independent equations, phi equations, theta equations, and r equations, then we solve these equations independently. We solve phi equations, we solve theta equations, and then we solve r equations. And since theta and phi are the angles, so we combine the solution of theta and phi angles together, and such combined wave functions is called, combined function is called spherical harmonics. These spherical harmonics one can plot, and one can get the shape of the s orbital, p orbital, d orbital, and all those orbitals. Okay, because the orbitals we define as the square of the wave functions, plot of a square of the wave function. So once you have the spherical harmonics, you can plot these spherical harmonics, and you can get the shape of the SPD and SPD orbitals and all those orbitals. Okay, so this was hydrogen, and simultaneously we plotted the r values also, the radial part of the wave functions also, and we have shown that 1s orbital has no node, but 2s orbital has one node, 3s orbital has two nodes, and that is decided by the radial part of the wave functions. Because for s orbital, what spherical harmonics which we obtained were not having any theta and phi. So we say, since s orbital wave functions, s orbital spherical harmonics does not depends on theta and phi, so it has to be spherically symmetrical. It has to be spherically symmetrical. Okay. Then after doing hydrogen atoms, we talked about the concept of angular momentum. And then in the concept of angular momentum, I talked about that you have a linear angular momentum, and this angular momentum concept is important in quantum mechanics because it gives you the idea of precessional motion of the moving electrons, moving nuclei. And there's a the spinning motion, the spin angular momentum. When you come to the spin angular momentum, this forms the basis of a spin resonance spectroscopy. And all of you are aware of electron spin resonance spectroscopy and nuclear spin resonance spectroscopy. Okay. So this concept of angular momentum was important, where I talked about how commutators define that we can obtain the absolute value of the angular momentum or any one of the component Lz, Lx, or Ly, which is normally taken as Lz by convention, so that you can find out Lz operators and L square operators can be obtained, and what is their eigenvalues, how it is obtained. We talked in details. Okay. Then also I talked about the concept of uh, this ladder operators. Ladder operators are operators by which you can raise or lower the eigenvalues or the eigenfunctions of the linear angular momentum operators. After talking about concept of ladder operator, I talked about in details the addition of the angular momenta, Russell-Sanders coupling, and the finding out the term and symbol. Okay, and then also I extended the concept of orbital angular momentum to a spin angular momentum also. And for a spin angular momentum also, we did the addition of the angular momentum, and we talked about the concepts. Okay. After finishing the angular momentum concept, we came to the system with more than one particle. Say, for example, helium atom or H2 plus molecule ion. And what I said you that when you write the potential for these systems, the potential which you write is quite big. Okay, and because of this, the hydrogen atom, the solution for these Schrodinger wave equations are not feasible. Exact analytical solution of Schrodinger wave equation is not feasible for helium atom, is not feasible for H2 plus molecule ion, is not feasible for H2 plus molecule. So exact solution one cannot obtain. And then came the concept of approximation methods. I talked about approximation methods, which was of two different types, variation methods and perturbation methods. In variation method, I said you that in variation methods, what we can do is in variation methods, we guess a trial wave functions, and from this trial wave functions, which we find out the energy of the ground state wave functions. And for that we have, if you remember, we have taken for, I'm not able to write now. We have taken x into L minus x as the wave function for particle in a one-dimensional box, trial wave function for particle in a one-dimensional box. So the details are there already available to you in the earlier weeks. You have done it. Okay. So in variation methods, we found that though the system is not solvable exactly, but using this variation and perturbation treatment, one can reach to the eigenvalues very close to the actual values. So approximation methods are not that bad. We can approximate the results for the higher systems also. So quantum mechanics is not restricted to only model systems of helium atom or hydrogen atom or SHO, simple harmonic oscillator, or rigid rotor. We can go beyond that also, and we can deal with the system which is more than one particle. Okay, using the variation and perturbation treatment. In variation methods, we take a trial function, and then from trial function we find out the energy value, and then you minimize that energy, and you get that minimization of the energy, you get the value of variation parameter. And this variation parameter is important because from this you can get the wave function also, and you can get the eigenvalue also. In perturbation method, what we say, we apply to those systems for which we have a system which is already known, for which the exact solution is available, and then a slight tweak in the system has resulted into a system which is unsolvable. So we say a system is perturbed system, a system is unperturbed system. Unperturbed system is a system for which solution is available. Perturbed system is a small deviation from the unperturbed system. So what we say is that if you have particle in a one-dimensional box, and if you put an this particle which is moving in a one-dimensional box into an electric field, then this will be a perturbed system. And one can apply perturbation theorem to find out the eigenvalues and eigenfunctions. And there are different levels of corrections: first order correction, second order correction, third order correction you can make. And if you find out the first order correction to energy, then first order correction to energy depends only on the wave function of the unperturbed system as well as the perturbation, which you are calling. Perturbation is very small quantity by which the system is perturbed. Okay. Having done perturbation theorem and approximation methods and perturbation methods, we moved on to the system which is molecular systems. In case of molecules, we have to apply this variation treatment. Then we talk about linear variation treatment. And we say that if you have H2 plus molecule ion, then for this H2 plus molecule ion, we can guess a trial wave function by saying that there is a probability that in H2 plus molecule ion, which has only one electron, that electron might be at some point of time at some particular instant with the one particular nucleus A. And at another point of time, it could be associated with another hydrogen atom B nucleus. So the wave function psi A and psi B, which is designating the two hydrogen atom psi HA and HB, both can contribute to the H2 plus molecule ion wave functions. So we say that H2 plus molecule ion trial function will be a linear combination of psi A and psi B. And to what extent each will contribute will be given by a coefficient. So we can add Ca and Cb for that. Okay. So the trial wave function psi trial will be psi A, Ca psi A plus Cb psi B. And using these trial wave functions, one can find out that the moment you do the variation treatment, you find that two energy level exist. And it means one is lower energy level, another is higher energy level. So lower energy level is called molecular bonding molecular orbital. Higher energy level is called anti-bonding molecular orbital. And corresponding to these two, we can find the wave functions also. Okay. So molecular orbital treatment is straightforward. One can do by combining the linear combination of atomic orbitals. An extension of the linear combination of atomic orbital and the variation treatment we did in the HMO case. At the end of the course, which has not yet come to you, Haeckel molecular orbital, where we talk about the butadiene molecule, the benzene molecule. So their pi electrons can also be treated by variation treatments. Okay. So this is again a further approximation for larger systems. HMO will come to you in, I think, in 11th or 12th week. So that we did. Besides this, concept of hybridization also we did. And I talked about SP, SP2, SP3 hybridization and how do we write the wave function for SP hybridization, for SP2 hybridization, for SP3 hybridization. Okay. So we covered right from the pre-quantum concept to the concept of this HMO concept. Okay, everything from applying postulates of quantum mechanics, then particle in a one-dimensional box, three-dimensional box, simple harmonic oscillator, rigid rotor, hydrogen atom, concept of angular momentum, Russell-Saunders coupling, okay, addition of angular momenta, ladder operators. After doing all these things, then variation treatment, perturbation treatment. Then we talked about this molecular orbital theory of H2 plus molecule and as well as diatomic molecules also I did. Okay. And then we talked about valence bond theory, then hybridization. Okay. After doing all these, the last two lectures will be application of quantum mechanics to quantum dot, where you will learn that how does quantum mechanics play an important role in recent researches also. Quantum dot is an important area of research, and so for this new research area, I invited one of my colleagues, and he has given the lecture. You will see in the perhaps in the 12th week that how it is applied to the quantum dots and what is the concept of quantum confinements and how do this concept of quantum chemistry, quantum mechanics is still applied to the systems. Okay. So any one of you who is present here? Any one of you? No one is present here? Okay, so I'm finishing it right now, but all learners are invited to ask questions on the websites. There's a question answer websites is already there, so you please post your questions, your queries. I will be happy to answer your queries as much as possible. Okay, thank you everyone.